So take a look at this following graph. If this is a position versus time graph, the question is, how could you actually make this graph? If you're driving your car, how could you do it? So again, think about this as being position on this axis, time on this axis, and most of you can sort of figure out real quick, oh, wait a second. That means that position has to be increasing at a regular rate. How would you do that? Well, you would just drive at a constant velocity away from the origin. Same thing with walking it. What about this graph? So this one, it's kind of interesting. Your position is decreasing with respect to time. How in the world would you walk this one out? Well, you'd actually have to head back towards the origin, starting out originally with a large position and then having a decrease at a regular rate, either by driving your car back to some origin or walking back towards some origin. What about this one? This one's a little bit stranger, the position versus time graph. As time increases, what's happening to your position? Well, your position's actually staying constant. How would you walk this one out or drive this one out? The answer is pretty simple. Just start some point in front of the origin at some positive position and then don't move at all. What about this one? And this is what we're leading into today, this kind of unusual idea of how in the world would you do something like this? Is your speed constant? In other words, is your change in position constant? And the answer is no. If you look at this, you're going slowly to begin with, and then your slope here is a little bit larger, and then your slope here is even a little bit larger, and your slope here is even larger. How would you walk this graph? Well, you'd start at some positive position. You'd start walking away from the origin slowly, and then can constantly pick up speed until you're moving very, very quickly. Finally, these couple last ones, how would you do this one? Well, you'd stand still for a while, then walk away at a constant rate, and then stop again, and that would give you that graph. This one, you'd walk away at some constant, away from the origin at some constant rate, and at this point here, you would speed up very, very quickly, and now your change in position with respect to time, the slope of the graph is larger. This would be delta x, the change in position. This would be delta t. And again, the slope of this is defined as velocity. At some point, we'll do this mini lab where I'm going to have you actually walk these 5 graphs out, but we'll do that a little bit later. So take a look at the worksheet 1. And I just want to walk through it real quick. Take a look at the position versus time graphs for these two people. We've got... here's cyclist B, starts out at the origin and moves, forgive me for my really bad drawing skills, along it like that. And then A is actually moving, starts out here, I thought I'd change colors, starts out here and then moves along this line right here. So the question is, do the cyclists start at the same point? And hopefully the answer is no. You can see the y-intercept here for A is some value that's not 0, whereas the y-intercept here for cyclist B is 0. Who starts ahead? The answer is cyclist A starts out ahead of time. At 7 seconds, which cyclist is ahead? Well, to answer that question, we need to look at about 7 seconds, probably somewhere right around here. And at this particular instant, who's ahead of the other one? Well, if you look at it, you can sort of see, oh yeah, cyclist B has a greater position than cyclist A. How do you know? They're simply further up the graph. Take a look at this question. This one's actually an AP level question. This time, kind of similar in a lot of ways. We've got masses P and Q. Here's the question, do P and Q ever have the same velocity? And if you think about it, same velocity would be, they would have the same slope at some time or times. And if you look at this, we have multiple choice answers. P and Q have the same velocity at 2 seconds. Well, if we look at 2 seconds, the slope of this one's this way. All right, 2 for this one might be the same if we draw a tangent line at that point. All right, maybe. I'll put a little check mark by it. They have the same velocity at 1 and 3 seconds. Well, at 1 and 3 seconds, they do cross each other. Does that mean that they have the same velocity at these 2 points? The answer is absolutely not. If you look at velocities, the slope of the graphs, q is going this fast, that slope, compared to this slope. No, the two slopes are very, very different. What is true at 1 and 3 seconds? They have briefly the same position, but they don't have the same velocity. B is a no. P and Q have the same velocity at 1, 2, and 3? No. We already know that 2 and 3, they have different slopes. 1 and 3 seconds, they have different slopes. C is definitely not true. P and Q never have the same velocity. Well, this is a possibility, but we know we have to choose one of these answers. Take a look at Q for a moment. If you look at Q, and I'm going to switch to red here, for object Q, its velocity here is greater than object P, and over here, its velocity is somewhat less than P. By logic, somewhere between 1 and 3 seconds, it must have the same velocity. So D cannot be right, leaving us with, by elimination, yeah, A is the correct answer. All the other three have to be false. Here's question 2. I know you've already done the worksheet, but take a quick look at it. Some people struggle with it. How does the motion of cyclist A in this case compare to cyclist B? Sorry, A kind of fell off of here. Cyclist A this time starts out at some positive position, and their position decreases at a regular rate. What does that mean about cyclist A? They're heading back towards the origin at a constant rate. So in this case, they're moving backwards is what's happening. How's the motion of B in this one compared to B in the previous one? In a lot of ways, I think it's similar. If I remember correctly, B started out at the origin and ended up over here. So yeah, it's also very, very similar. Which cyclist has a greater speed? That's the magnitude of velocity. Well, to answer this question, we have to think about the slopes. Basically, we're looking which one has a greater slope. In other words, covers a greater distance in the same amount of time. So this one is delta x for this one here for cyclist B. Here be delta t. And if we look at the exact same time interval for the other one, same time interval for the other one, we discover that, oh wait, for this one, delta x would only be this during that same time. Here's delta t. Which one of these has a greater velocity, greater slope, magnitude? The answer is B has a greater displacement each unit time than the other one. So who has the greater one? B is greater than A. What in the world is happening, though, at this intersection? You're like, oh, they have the same velocity at that moment right here. The answer is no, it's not the same velocity. What do we know? Their positions are the same. They briefly have the exact same position. Sorry, it takes me longer to draw this than it's worth. All right, moving on. We've been talking about position versus time graphs, and we're going to move into velocity versus time graphs. So take a quick look at this. Be careful. This is position versus time. Look at your labels here on the axes. And over here we have velocity versus time graphs. So we've talked before about walking these. Which one of these velocity versus time graphs out of these four, A, B, C, or D, would correspond to this? So how would you walk this one? Well, we've talked about it before. You would actually stand still. So what would be your velocity during this? It would be actually 0 the entire time. You would not have any change of position with respect to time. So B is the right answer on this one. What about this one? Your position versus time is increasing at a regular rate, which means you would walk away from the origin at a constant speed. So what would your velocity versus time graph look like? Well, if you're graphing the velocity, we would have a constant positive velocity. It should be a graph that looks something like this. C is the correct answer this time. This one. This one's a little bit more interesting. What's happening? We've talked about this before. You'd have to walk at a faster and faster rate. What does that mean is happening to your velocity? It's going to have to increase with respect to time. And I hope you can sort of see, oh yeah, D would be an increase in velocity as time increases. This one. We haven't talked about this one yet, but think about it for a brief moment. You would start walking away from the origin at a fairly rapid rate, and then that would get smaller and smaller and smaller. What does that mean is happening to your velocity? Well, it's positive the entire time, but it starts out with a large magnitude and then becomes less and less positive. That graph is going to be graph A. Worksheet 2 is one that you're going to have, or you're going to be drawing tonight, where you're drawing not position versus time, but velocity versus time. So in this case, we're going to be drawing these. An object is standing still. What does it mean its velocity is going to be? Well, it should be constantly 0. In this case, the graphs will have positive and negative ends. 0 should be right in between the two. Car moves towards the origin at a steady rate for 10 seconds, then stand still for 10 seconds. If you're moving towards the origin, if you're on the positive side, that would mean you have a negative velocity because you're heading back towards the origin for 10 seconds. I'm going to put 10 on here. And then you're going to be standing still for 10 seconds. So all the way out to 20 seconds, you have no velocity. Now, for those of you who are smarty pantses, you might say, well, wait a second. Couldn't your position versus time graph look like this? And let me quick draw it. There is a second answer for this one. It could be that you're actually starting out on the negative side. So you're starting out somewhere here. You're moving back towards the origin. You would actually be doing this and then standing still for 10 seconds. So again, this is our 10 seconds, here's our 20 seconds. In that case, your graph would actually look like this. You'd be positive because you're gaining, you're heading, this is a positive slope over here. And then you'd be 0 down here. You're like, well, wait a second, how's that compared to the other one? The other one, we would start out positive and move back towards the origin for 10 seconds, then stand still. This would produce our red graph over here. The blue graph could be that one. Either one of these is fine. Number 4, object moves away from the origin at a steady velocity for 10 seconds, reverses direction, and then moves back at the same velocity. What should that look like? Well, it should look something like this. Moves away from the origin, and maybe I should draw a position versus time graph, just so you can sort of think about it. Moves away from the origin at a constant rate for 10 seconds, and then heads back at the same velocity, but now negative. It should look like that. So here's our 10 seconds, here's our 20 seconds. It would look something like that. What's our velocity versus time graph going to look like? Well, we'd have a constant positive velocity for the first 10 seconds. And then we'd have a constant negative velocity for the next 10 seconds until we get to 20. Is this the only answer? Oh, a lot of people want to know, do you connect these? You can put a dotted line in between there if you want, something like that. Is this the only answer to this one? The answer is no. You could also do this. You could move away from the origin at a constant velocity in the negative direction for 10 seconds, and then move back towards the origin for the next 10. What would that graph look like? It would look like this, just in reverse. You'd actually end up with a negative velocity here, negative slope, and then you'd end up with a positive velocity. Sorry, 2 dotted lines on top of each other. And then you would be over here, and pretend that's the same height. Hopefully that makes sense. The last part of this one, they actually give you the position versus time instead of giving it to you in words, and you actually numerically have to solve it. So take a quick look at this. What is your velocity during the first 1 second? Well, you covered 2 meters in 1 second. So your velocity here is going to be 2 meters per second during the first second. What's your velocity for the next part? Well, if you look at this slope, we gain 1 meter here for every 2 seconds here. What's the slope or your velocity? You drop down to 1/2 meter per second, all the way from here out to 5. Pretend I actually drew that straight. Yes, you can, if you would like, make a dotted line here, but it's not required. And then finally, this last one. If we look at this one, the slope for the first 2 seconds, you gain 2 meters in 2 seconds. What's your velocity? Well, velocity, again, displacement over time. 2 meters over 2 seconds means that for the first 2 seconds, you're going at 1 meter per second. And then finally, what's the slope over here? I'm going to change colors just to avoid confusion. If you look at this point here and this point here, it's there in 1 second, we lose 2 meters. The slope of this one is negative 2 meters over 1 second. We go negative 2 for the next piece. And we technically end at 4 seconds here, so we'd end there. And again, optionally, you can put a little dotted line on there. Hopefully that'll give you enough information to be able to solve that one. Motion maps. Motion maps are kind of fun. I like graphs, but some people love motion maps. A motion map, simply you draw the position of an object and you plot it every second. Imagine you had a strobe light in a dark room that was just flashing once per second, and a person was walking across the room. You would see that person first here, and then you'd see them 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 here. Just by looking at this, what can you tell me about that person? They're covering the same displacement every second. Their velocity is constant. But what about this person? 1 second later, they're here. Next second, they're here. Next second, they're here. Next second, they're here. What's happening to this person? They must be gaining speed or gaining velocity in the positive or right direction. What would happen if you saw this one? This one, hopefully you'd recognize, oh, wait a second. What's this person doing? They're slowing down. In the first second, they go this far. Second second this far. Third second this far. Fourth second this far. They're not covering as much distance each unit time. They're slowing down. Still moving in the positive right direction, but they're losing velocity. Physicists tend to be lazy. They won't actually draw people or the object every single point. They'll simply draw a dot to represent the position of the object every single second. Is this object speeding up or slowing down? I assume that most of you will say, oh, it's speeding up. Why? Because the distance between each one of these dots is getting greater and greater and greater and greater and greater. But this is with the assumption that the object is heading this direction. It's also possible that it was actually heading towards the left, in which case it started out here, a moment later it was going here, and then it only covered this distance here, and then this distance here, and this distance here, and then even less here. It could be slowing down as it's heading in the negative direction, the left direction. So when we switch to dots, there's one thing that we always do. We'll draw a little vector that represents that object's velocity at any given instant. And it's always representing the upcoming second. And so this is a velocity vector showing how fast and in what direction the object's moving. Now there's no confusion. In this case, we know that, this first guess that we had that it was speeding up is correct. This one is wrong. And you can even do some calculations on it. So take a quick look at this one. Here's a motion map. The question is, rank the magnitude of the average velocity over the first 3 seconds. So we'll assume here we start out at 0, and then here's 1, 2, and it's moving this way. 1 second, 2 seconds, 3 seconds later it ends up here. What's the average velocity of this one? Well, it covers 6 meters in 3 seconds. Its average velocity is 2 meters per second. What about B? Well, it starts out here. 1 second, 2 seconds, 3 seconds. Oh, in this case, it covers 2 meters in 3 seconds. We end up with 2/3 of a meter per second. C starts out here. 1, 2, 3. It ends up here. It covers 9 meters in 3 seconds. And so its average velocity is 3 meters per second. And you can sort of figure it out real quick and even do the last one. Be careful on this one. You're like, okay, starts out here, 1, 2, 3. Oh, this one goes 10 meters. This one was the fastest one. Well, it does do it in 3 seconds. But did it go 10 meters? Well, it actually started out at 1, ended up at 10. Its displacement, 10 minus 1, is actually 9 meters. And so its velocity is still also 3 meters per second. So ranking these, what's the order? A is equal to C. They're both the winners. That's greater than A, and that's greater than B. B is our slowest one. Good. You can also do motion maps in multiple directions. In this case, they didn't draw an arrow on each one of these. They just drew an overall arrow. What's the average velocity in the last time interval? So for this one, it starts out here, ends up here. We don't have numbers this time. Here it starts out here and ends up here. Here it starts out here, ends up here. And this one starts out here and ends up here. You'd have to get a ruler out probably to compare D and A. But just looking at it, these all happen in 1 second. Which one of these is greatest? A and D actually are identical. The displacement's the same. Followed by B. And then at the end here is C. It has the smallest displacement, change in position, delta x, of all of these. And finally, you can actually draw motion maps off of graphs of this type. In this case, warning on this one, time is over on this axis, so be careful. At t equals 0, its position is 0. That's this one right here. At 1 second, it's at 2 meters. At 2 seconds, it's at 4 meters. Now, here's the issue. How in the world do you draw this when it stays at the same spot? So here's 2 meters, here's 4 meters. We just did this one. We're about to do 3 seconds where it's also 4 meters. You could draw the dot on top of itself, but that really would not indicate it. But please remember this is a one-dimensional number line where x is over pointing this direction in meters. So what you can do on this one is actually stack. So here is the second one right here. Now ends up also at, both of these are at 4 meters. There is no y direction in this case. And then at 4 seconds, we're at 7 meters. Then at 5 seconds, we're at 10 meters. Now, one little note on this, and you probably saw it already. Once you start stacking, we tend to stay at that same level. So we just move upward a bit. And then we stay at 10 meters for the next 2. So now here's the 3 of them all at 10 meters. And then at 8 seconds, we go backwards. And again, we're going to stay at that same level. So here we are back at 5 meters. And then we go back at 9 seconds, we go back to 0. What is the one thing that's missing from this? I would go ahead and add in, and then real quick question. If we put in 10 seconds, it's back at 10. Normally you're already at this level. If you drew the 10, you'd be right here. That next 10's got to go up here. So what we usually do here is this. We'll actually move that one up just so it lines up with that one. And you'll see why here in a second. If we add the arrows, now it all kind of makes sense. These are the velocity vectors for each single point, and it tells you the direction it's going, and the size of the velocity vector is proportional to the velocity. And so we get some nice results. So in worksheet 2.4, we combine all these ideas together. Not only are we going to create a position versus time, we're also going to create a velocity versus time and a motion map for this object. So first of all, graphing the different points. We've started at 0. At 1 second, we're at 2 meters. At 2 seconds, we're at 4. Then we stay at 4. Then we go to 7. Then 10. We stay at 10 for 2 seconds, then down to 5, and then finally back down to 0. So there's our position versus time graph. I'll connect the lines the points just a second. But now let's take a look and figure out velocity. Well, in the first 2 seconds, we gained on average 2 meters for every 1 second that we went. If you look at this right here, 2 meters for every 1 second. That means our velocity during the first 2 seconds was 2 meters per second. This is our 0 point here, so each unit is 1. 1, 2, 3, 4, 5. This is 5 meters per second. This would be negative 5 meters per second. During the next 1 second interval, we don't go anywhere at all. So our velocity between 2 and 3 seconds is 0. For the next 2 seconds, we gain on average, if you look at it, 3 meters for every 1 second. So our velocity during this part is 3 meters per second. Oops, sorry, going forward. And so we're going to put it at 3 meters per second between 3 and 5 seconds. Next 2 seconds, we're stationary. So we're going to back down to 0. And then the next 2 seconds, we actually lose 5 meters for every 1 second. If you figure out the slope, rise over run. So our velocity is actually going to be at negative 5 meters per second. And so we'll end up with something that looks like this. Yes, you can connect lines or you can make dotted lines between these to make it a little bit easier to visualize, but that is optional. But you get the idea here. Finally, we have our motion map. The motion map, we're just going to plot the position at each and every moment. At 0, we're at 0. At 1 second, we're at 2, 4, 4 again, so we stack it. Then we're at 7. We stay at that same level. Then we get to 10. And my apologies, we'll call this over here 10 meters. Sorry, it's not quite long enough for the work we need to do. Then we stay at 10, so we just keep stacking upward. And then we go back to 5. Now 5, we're going to stay back at that same height. I guess I should label some of these. This is our 0. There's 5. There's 10 meters. And then we go back to the start. The one other thing we need to add for the motion map is usually, again, just to make sure it's clear to everybody, we'll add little arrows to indicate what's happening at each and every single moment. And you can just draw these with these. These are our little velocity vectors. Their length is proportional to the magnitude of the velocity at each moment. Again, notice that these are the last two are pointing backwards, which indicates again that it's that negative 5 meters per second. And now we're going to a different one. We've been talking about the slope of a position versus time graph. What does the area underneath a velocity versus time graph give you? So think about this one real quick. The area underneath this, well, before we get there, if you go 30 meters per second for 6 seconds, how far do you travel? And the answer is, well, you're going 30 meters every 1 second. So at 6 seconds, it should be 180 meters. Well, if you think about it, that's also the area underneath this graph. In this particular case, the area is 30 meters per second, the height is 30 meters per second. The width is 6 seconds this way. And if you watch your unit, something interesting happens. Seconds cancel, and you'll end up with just 180 meters. So here's our big idea. The displacement underneath a velocity versus time graph, has to be velocity and time, is always going to give you the displacement, the change in position of an object. Does it mean this object's at 180 meters when we get done at 6 seconds? No, it all depends on where it started. If it started at 10 meters, it'll be at 190 meters away from where it started, or the origin. In this case, this again represents the displacement of this object. In this case, the object started out at 40 meters per second, and by 4 seconds, it dropped down to 0. How do you find the area of a triangle? Well, hopefully most of you remember it's 1/2 base times height. Again, seconds cancel, and you'll discover in this case the displacement of this object, delta x, is going to be 80 meters. And you're like, oh, okay, not so bad. Yeah, in this case, this object will have moved 80 meters in the positive direction. Depending where it starts, yeah, it all depends on its ending position. What about this one? Now, this one could be a little strange. Turns out this is the same as before, so the displacement here is positive 80 meters. But what in the world is happening over here? Well, unlike math classes, in this case, the velocity over here is negative 40 meters per second. If you do that for, and again, it's 4 seconds wide this way, this displacement over here is actually going to be negative 80 meters. And we never talk about negative areas in math, but in physics, it doesn't actually make sense. What's the net displacement of this object? The answer is 0. You gained 80 meters, but then you lost 80 meters. You ended up back where you started, wherever that is. Finally, what if you have something like this, a trapezoid? There's a couple ways of solving it. One is, if you happen to remember it, the area of a trapezoid, 1/2 base times h1 plus h2, where that's the two heights here. Or you can also take the area of this whole area, triangle, all the way out to here, and then subtract this triangle that's in here. Either way will work. And then just subtract this piece here. You know the rule for the area of a triangle, you can easily solve it. In this particular case, if you use the top equation, the displacement here, or the total distance traveled, will be 150 meters. You'd also get the same answer if you did the subtraction of the two triangles. Alternately, you can also do this trick, and I just want to mention real quick. You could draw a straight line across this, and now our trapezoid is just a rectangle and a triangle. And you can use that to solve it as well. In this particular case, the area of this down here is 20 meters. It's 2 wide, 10 tall. And this one is 2 by 20 times 1/2. 20 by 2, yep, times 1/2. This one's going to be 20 meters. What's the total displacement of this object? It would be 40 meters. And, yeah, in general, you can come up with an equation for this. We'll talk more about this later. And you can come up with a kind of general equation. Displacement, initial velocity plus 1/2 final velocity minus that. Or eventually, you could write it that way if you combine terms. Or in general, this one. I do like this one. And you might say, wait, what in the world is this term? Well, initial velocity plus final velocity by 2, this is really just the average velocity. So if you take the average velocity times the time you travel, you'll get your displacement. What's the displacement of this one? You're like, oh, okay, just the area underneath the curve. I don't know if there's a good way of doing this. Probably the best way to do it is just count up all the squares, and then you're going to have to do some estimating. Like, oh, this looks like half a square. Here it looks like half a square. And do some really good estimation over here, maybe 1/3 of a square. You can add it all up to here, but you'll end up with some negative displacement. Just, again, remember this is a negative area, and you could solve it. Oh, we got a brain break. What's for breakfast? From each word below, remove one letter and then rearrange the remaining letters to form something you might have for breakfast. If you want to try this one, hit pause on the video real quick. Otherwise, I'm about to show the answer in 3, 2, 1. Cleaner becomes cereal. Gamble becomes bagel. Telecom becomes omelet. Tribute can become butter. Carbon can become bacon. And meatloaf can become oatmeal. I know you might say, I don't know if I eat butter for breakfast. Well, it's something you can use at breakfast. And then just a brief introduction to acceleration. Acceleration is the rate of change in velocity. It's defined as delta v, the change in your velocity, divided by delta time. Or you can kind of solve it that way. Sometimes you get interesting graphs. Up to this point, we've always had straight line graphs, if you remember the one we'd started with. But you can even talk about the slope of a point right here. How do you find the slope of the blue graph at this point? Well, you draw a tangent line to it and then figure out the slope of this tangent line. And that'll tell you the acceleration at that instant. Again, the slope, delta v over delta t, is rise over run in this case. The slope of velocity versus time graph will actually give you acceleration. Oops, finished writing that. There's a graphic relationship to this one. Let me show you. If you have a position versus time graph, and you start drawing little tangent lines to find the slope of this, notice what's happening to the slope of each and every line. The slopes are getting greater and greater and greater. Please remember that the slope of a position versus time graph gives you velocity. In this case, the velocity starts out at 0 when the slope is 0, and then it gets greater, greater, and greater. What should this graph look like? It should be a straight line. Then, how do you find acceleration? Acceleration is the slope of a velocity versus time graph. Can you tell me something about the slope? Well, if you draw little tangent lines to this one at every single point, you'll discover the acceleration is constant and positive, meaning this graph looks like this. In general, here's how you solve this. The slope of the position versus time will give you velocity. The slope of a velocity versus time graph, oh, I actually did it on here, sorry. Drew some lines. I probably see how close I came. Yeah, pretty good. And the slope of that will give you the acceleration. In this case, the slope at each point is constant, and so you'll end up with that. And if you draw a line through that somewhere there, I'm going to remove my line because it's not as pretty as my other one I drew. And you can very quickly solve this. How do you work backwards? Well, if you remember, the area underneath the velocity versus time graph will give you delta v, and the area underneath velocity versus time will give you displacement. Take a quick look at these. You're trying to figure out the magnitude of the change in the velocity. Magnitude means we don't have to worry about positive or negative. In this case, what's the change? Well, the change in is final minus initial. Final 20 minus initial 10. Delta v in this case is positive 10. What about this next one, b? Your final is 0. Your initial was 10. 0 minus 10 means delta v in this case is going to be negative 10 meters per second. I'm leaving off units just because it's hard to draw. What about this one? And I want you to think about for a brief moment. The final velocity was negative 10. Negative 10 minus the original 10, change of velocity negative 20 meters per second. And the last one, final is 20, first one's 10. Delta v in this case will be negative 10. You lost 10 meters per second. Ranking the magnitude, ignoring positive and negative signs, what happens? Well, it turns out C is the greatest, followed by A equals B equals D. Those are all 10s. Your last worksheet tonight is going to sort of tie it all together. You're going to be given one of the three things and try to figure out the other parts. So in this case, what's the object doing? It starts out here at some positive position. It has some positive velocity during this part, then it stops, and then it goes backwards. If you grab or draw your velocity versus time graph, it's going to be positive for the first part, roughly the same amount of time as we have here. I'll try to draw it here. Then it stands still for a while during this top part up here. That means its velocity is going to be 0 during that. And then this next portion here, it has a very large negative slope, a very large negative velocity. Written description, sorry, I'm not going to try writing this one. What did our object do? It started somewhere in front of the origin, moved away from the origin at a constant rate, stopped for a while, and then moved back towards the origin for a longer period of time. Motion map. You don't have to draw too many dots on this, but what should this one look like? Assuming this is our 0 point or origin, it should start in front of that, move away from the origin. I'm going to go 2 units every single time here. And this is qualitative, so don't stress. Then it stands still for a while, and then it moves backwards at a more rapid rate until it's basically almost back at the origin. Again, don't forget to put your little velocity vectors on this one. So it went this way. Sorry, my arrows are not real pretty. And then back, and then back. So something that would look like that. Okay. You kind of get the idea. Let me do one more, maybe one from the other page. Okay, let's go from a motion map backwards. So in this case, the object starts out somewhere ahead of the origin. It moves backward at a constant speed, stops for a while, and then moves forward at a slower speed. What would the velocity versus time graph look like? It would be large and negative for the first couple of seconds. Then it would stop for a while, and then we have a positive velocity but at a slower rate for a longer period of time up here. Pretend those are horizontal lines. What would our position versus time graph look like for this one? It would start out away. I assume that the origin is somewhere over in here. It would start out away from the origin, move backwards at a fairly rapid rate, constant slope, then stop for a while, and then move away from the origin at a slower rate. That's our positive slow velocity, something like that. And the word description is what I mentioned. What happens if you have two objects? So take a look at this one. Let's look at the final one here. Looks like A starts at the origin. And so in this case, I'm going to draw two lines. Here's A, moving away at constant speed. How do I draw B? Well, B starts somewhere away from the origin, but then it seems to be going the same displacement each second. It's not that B starts later, it just starts. This is t equals 0 for this one, or this is t equals 0 for A. So they start out at different positions. So B is going to start out somewhere here, but it should be gaining position at the exact same rate. These two lines should be parallel. How do we draw their velocities? Well, they both actually have the same velocity, and they both start with that velocity at 0. So it turns out, to draw this one, it gets a little bit weird. Both A and B are on top of each other. And I'm going to have a tough time trying to draw this. It's probably going to blank out one or the other. A and B both have the exact same velocity. Description? A and B both move away from origin at a constant or the same constant speed, but A starts at the origin, B starts at some positive position. That should take you through tonight's homework. Good luck working on it, and I'll see you soon.